So this is going to be an introduction to WebRTC with libp2p. And I want this to be an interactive workshop. So feel free to interrupt me at any point. Just raise your hand and we can address any questions you have. But before we get in, I have the sense that a lot of the people in here are very familiar with this stack. So I'm not sure how valuable this will be, but maybe it'll expand your theoretical understanding of some of what's happening behind the scenes. And possibly this will help newcomers to libp2p who view this later on. Okay, so there's three goals that I think that I think it's important we set for this workshop. The first one, to understand why WebRTC and where does sort of libp2p come into this. Why would you use libp2p with WebRTC? Understand some libp2p concepts and how they relate to WebRTC. And finally, we're going to actually work through the guide and establish WebRTC connection between two browsers on your local machine. I know that's not very exciting. The reason we're going to do that is because the network that we're on is constrained. So there's host isolation, which means we can't even dial each other. We might be able to do that over a public network, even though I highly doubt it, but we'll see how we go. We'll first try to do that, have an understanding of what's going on, and then we can try to do that maybe over a public network. Okay, so why WebRTC and libp2p? First of all, let's start with why WebRTC. Here's a list of some of the transports that are available, with the exception of TCP. These are the three transports that we have available in browsers today: WebSockets, WebRTC, and WebTransport. WebTransport isn't actually implemented in Safari yet. So really, you're probably familiar with WebSockets and WebRTC. TCP obviously is not available. So WebSockets is probably the very established one. However, it was intended for client-server communication. So you can't dial browsers with it. WebTransport, which can be thought of as the evolution of WebSockets, is actually built on top of Quick, and runs in browsers and runs in workers, and we can think of it as the evolution of WebSockets. Okay, so that leaves us with WebRTC. WebRTC is the only way to establish connections directly between browsers. And of course, you don't need certificates. Another fun fact about WebRTC, we're not going to touch on it too much today, is that you can use it in order to dial servers too. libp2p actually has a spec for this called WebRTC Direct. And we're going to focus on just the standard vanilla WebRTC. Okay, so why libp2p? WebRTC is quite complex. It has a lot of different... okay, am I too close to it? Or... okay, all right. Yeah, okay, so WebRTC is quite complex. And as I mentioned, it mostly just encompasses browser to browser. The nice thing about libp2p is that it actually encompasses a lot more than just browser to browser. So, for example, if you're building custom protocols on top of libp2p and you want to use them beyond just the browser, then you might want to use libp2p. A great example of that is Gossip Sub. So if you're using Gossip Sub and you have some kind of a mesh network that involves multiple runtimes, then really you sort of lean into the benefits of having all of that interoperability across runtimes. And of course, as we'll see in a moment, libp2p actually implements decentralized signaling. So the WebRTC standard defines all sorts of tools for doing NAT traversal. These are called ICE, Interactive Connection Establishment. And as part of ICE, you have stun and turn servers. And these are sort of prerequisites for doing all of this NAT hole punching. However, signaling is something that is left to the user to implement. So there's some libraries that exist out there. I believe one of them is called Peer.js, which essentially implements like a standard client-server style signaling server. And the idea there is that you essentially create like an SDP candidate and you use this signaling server like a central point in order to do the coordination. What's cool about libp2p is that libp2p leans into circuit relay v2 in order to do signaling, and because today it's pretty easy to find circuit relay servers that can help you relay your traffic, essentially the coordination point, that signaling server, can be any peer that supports circuit relay v2, and I'm sure that we have some probe lab statistics that will show us that we have quite an abundance of them. So decentralized signaling is the TLDR for that whole blurb of mine. Okay, now I already sort of hinted on these additional servers, and the main idea here is that even if you want to establish the direct connection between two browsers, you still need all of these other servers that assist you in that establishment. These include stun servers and turn servers, and of course the signaling server that, as I mentioned, is not something that is specified by the spec, but the idea is that it's just used as a coordination point to exchange these SDPs, which are like a block of metadata about your observed address and what you can be dialed on, like what port and so on, so like your network information as it's observed externally. So kind of like what you get from identify in libp2p. Now the stun server, as I mentioned, it's part of the WebRTC spec. It's pretty cheap to run, but because it's so cheap to run, there's quite a lot that are publicly available that you can use. In fact, we have them at this point already pre-configured. We have a bunch of them pre-configured in JS libp2p. And then turn servers are where things get a bit more messy. So almost any NAT hole punching attempt, which is necessary when you're behind, say, a NAT or a firewall, you don't have a guarantee that that's going to succeed. So I think there's like statistics that say that success rates are anywhere between like 70 to 80%. And so in the cases that you're unable to establish a direct connection, you might want to use a turn server. The problem with turn servers is, first of all, they're relaying all traffic, so they're quite expensive to run. And of course, they require, if you run one of them, you don't want to expose it to the whole web, because then it's prone to abuse. So you need authentication, and the moment that you start having authentication for a turn server, it sort of takes away from like the flair of doing things in a peer-to-peer way. So I'm not going to sort of get too much into turn servers, but just to give you a concrete example of what like a stun server does, there's this great, there's a bunch of WebRTC samples here on GitHub. And I'm going to show you what it looks like to make a request to a stun server. And so this is like the stun server configuration. And if I do gather candidates, you can see that it actually, I was able to get my both the private IP and the IP of the public network. I believe that's the IP. I can try ifconfig.me. Yeah, so that's indeed the public IP that is being detected using this WebRTC. So if you're familiar with Identify, pretty similar, but part of this, part of the WebRTC spec, and this is implemented by all browsers. Okay, let's go back to the slides. Okay, so those were all of these servers that we need. In our case, for the signaling server, we're just going to find, in this guide, we're going to obviously just use this local bootstrapper, but in a sort of more production scenario, you might want to just walk the DHT and find them, or just run one bootstrapper that has circuit relay and is hard-coded into your application. So if there's anything you can take away from this, Actually, before we get into this, I wanted to make another note. So before this talk, there was a question about WebRTC and using that for video. So a big part of what makes WebRTC complex, beyond just all of the NAT hole punching magic, is all of the all of the video and audio encoding capabilities. So WebRTC supports multiple codecs, and it has, I think, like adaptive bitrate adjustments, and that adds a lot of the complexity. With JS libp2p, while JS libp2p, or libp2p broadly speaking, helps you establish the WebRTC connection, it mostly relies just on data channels. So WebRTC allows you to just create arbitrary data channels, and these are duplex streams that you can use for whatever you like. We, of course, with libp2p, you can build custom protocols, or you can use any of the existing protocols that are essentially running over this this data channel. Now, this data channel is also multiplexed. So in a similar way to how web transport connections are, or quick connections for that matter, are natively multiplexed by the transport, WebRTC also implements its own stream multiplexing. So there's no need for YAMX, except for when you actually need it. As we'll see, it's a little bit confusing, but we'll make sure that it becomes crystal clear. Okay, so I mean, if there's anything you can take away from this talk today, it's this whole gigantic diagram. As I mentioned, right, we have these additional servers that we're going to rely on. A stun server, we're not going to have to run it ourselves. There's a load of them that are publicly available. And what is actually in this diagram, a relay, I think we can call it a relay, we can call it a bootstrapper. And we've got a hand up from Nico. Yes, Nico.
I have been doing WebRTC more than 10 years ago without all the libp2p.
Yeah.
And I know all stun and turn and all of this very interesting time, as I remember. Yes, sorry. Stun server. Yeah, how is the situation today with stun servers? Because I have been working with stun servers more than 10 years ago, or around 10 years ago, from corporate LAN policy. Is it still at the old times? It was often not available, or you could not request any stun servers from internal networks because corporate LANs, for example, weren't allowing it, and then Turn was taking over and was maybe working or probably working, but then you had the last possibility to use HTTP or something, which I never used. But but what is your experience? Do you have any? Is it improving from a firewall policy perspective, or is it getting worse? The stun turn
it's a bit
situation?
hard for me to say because I imagine that it's blocked essentially by blocking host names or specific IPs. I don't know, actually. I don't have a definitive answer to your question about how it's getting blocked. Yeah, it's hard to say. I think working like from adversarial networks can be a challenge for any peer-to-peer application. I mean, as I mentioned before, even the type of NAT, so there's like, I think it's called a full cone NAT that becomes a problem for NAT hole punching. I can't remember all of the technical terminology for the different types of NAT mappings that you have, but it's working with this kind of like peer-to-peer from browser is like you're working on, you have to work with the assumption that you're going to have something like a 70 to 80% success rate. And depending on the situations and the kinds of applications that you're building, you should probably keep that in mind and try to adapt your application for it. But if that fails, then you sort of, and it's important for you to still maintain that peer-to-peer connectivity, then turn servers are the solution. Another approach to this, and I would love to hear, I think this is something that we probably need to research a bit more, but from my testings with the universal connectivity app, just relying on gossip sub to relay messages worked well enough. So as long as you're able to establish a connection to someone, it doesn't have to be another browser peer. It can be just a relay that is also listening onto the topic that's important for your application. Then you're still able to get your messages propagated. Does that somewhat answer your question? All right. By the way, this diagram is also on the WebRTC spec in the libp2p specs repository. But the main idea here is, the main idea here is that you have a relay. This is a libp2p node. It doesn't have to be JS libp2p. It can be Go libp2p, a Rust libp2p. In fact, in the repository that we're going to follow as part of this workshop, we have also a Go libp2p. The idea is that you want the browser to first, so you have two browsers, right? This is peer 1 and peer 2 in this diagram, and they want to connect to each other directly. In order to do that, one of them has to first connect to the relay. This relay is going to act as the signaling server. And after the first peer is connected to it, it'll ask for a circuit relay reservation. So what is circuit relay? Actually, let's back up a bit. So it's going to ask for a circuit relay reservation, and essentially that will allow peer 1, which is running on a browser which isn't publicly reachable, it'll allow it to become publicly reachable from the public internet, as long as, of course, this relay is publicly available. So that means peer 1 connected to this relay, and then suddenly anyone in the libp2p network using libp2p can connect to that peer and have all to the relay peer and have the traffic routed to peer 1. Of course, because it's circuit relay v2, it's a resource constraint, so it's time and bandwidth constraint, but it's just good enough in order to do this signaling, this SDP exchange. So coming back to the diagram, this idea that you have, first of all, a listener. So we can think of the dialer and the listener being both browsers. The listener first establishes a connection to the relay, gets a circuit relay reservation, and then the dialer can connect to the relay, and then using the relay's circuit relay reservation connect directly, well, not directly, connect to the other browser via the relay. That allows them to essentially communicate with each other. Once they're communicating with each other, they can discover each other's essentially WebRTC multi-adders, and that is all that is necessary for them to each initiate this whole RTC peer connection and basically the whole standard WebRTC connection establishment. And once they do that, they initiate this WebRTC signaling protocol that is over the libp2p relayed stream. And then they start sending the SDPs to each other. And then they call the stun server. The stun server tells them their public IP. And then essentially they're adding these candidates using the local sort of WebRTC API in the browser. And then they try to dial each other directly, and once they do that, then the noise, so once the connection is established, then there's a noise handshake that happens in order to authenticate the peer. Okay, I know that that was quite a mouthful, but let's break that down. Okay, so I know that was a lot of talk, a lot of technical stuff, and I thought I should probably clarify a bunch of things. So very, very basic things. libp2p concept. So we have peer IDs. So a peer ID is how every libp2p peer is identified. Typically, they're derived from the public key. Luckily, ED25519 public keys can be inlined. And so essentially, your peer ID, if it's an ED25519, is the public key. So you don't need to derive it. You can basically get it. And that key pair is used to sign almost all messages that you're sending. This is a fundamental part of how everything is authenticated in libp2p. And of course, a peer ID can have multiple string representations. So obviously, normally it's stored in a binary format, but sort of the first one that we see up there, I believe is a base 58, the one that starts with 12D. I believe it's the base 58 BTC. But you can also represent it as a SID. And as a SID, it's, I believe that's a base 32 SID. And it starts with buff Z. Anyways, you can sort of play with this on cid.ipfs.tech. You could sort of switch around the representations, or you can use even like the Kubo CLI, or of course do this programmatically. Okay, so we have peers. We have peer IDs, and a peer ID is a stable identity. And of course, because each peer can have can be connected to multiple networks, it can also roam across networks. Then we have multi-address. So each peer ID can have multiple multi-adders depending on the networks that it's connected to. And multi-adders are a uniform addressing scheme for multiple network protocols and abstractions and transports. So for example, we have here, for example, this peer ID that has two multi-adders. So multi-addresses are just sometimes abbreviated to multi-adders. And the difference between these two is that one is a quick one and one is a TCP one. So you can see, and does anyone know why it's quick v1 and not just quick? Just a fun fact. Any guesses?
Wasn't there a protocol change or something?
Yeah, so there was a protocol change. So actually when quick was first implemented in libp2p, the spec I think hadn't been fully ratified yet, and then there were some changes that had to be made, and we had to like add the v1 suffix. Hopefully there won't be v2, but I believe that there will be a change to the web transport one, because web transport, which is also over quick, hasn't been finalized. Anyways, this is giving us the main idea here is that it gives us the flexibility to adapt to new features. And so we can also represent things like certificate hashes and also relayed connections. So what do I mean by that? Let's go back to the diagram. So imagine peer 1 is a browser, connects to a relay, gets a circuit relay reservation. That's helpful. Why? Because it's now publicly reachable via the relay. How do we represent that? Well, we can represent that in the multi-adder. I'm trying to see if one of these, yeah. So if you see the P2P here, actually, sorry, I might be wrong about this. No, I don't think that's right. We will see it later. Oh, P2P circuit, that's the one. So if you have P2P circuit, that means that it's a relayed connection. I'm like 95% sure about this, but yeah? Yeah, okay, good. Yeah, so the P2P circuit is a way to like sort of indicate that this is a relayed connection. So this IP that you see here, the one that ends with 157, is not in fact the peer of the IP of the browser, it's the IP of the relay that you're going to connect to that is going to relay the traffic to that peer. And it's also why we have the peer ID of the actual browser that you're connecting to in that address, in that multi-adder. Okay, so I think I've covered multi-adders, peer IDs, circuit relay v2. I'll just make sure, yeah, exactly. As I mentioned, the P2P circuit protocol in the multi-adder, it identifies that it's a circuit relay connection. This multi-adder is a bit confusing because, as I mentioned before, you can actually use WebRTC for client, so for browser server connections. In libp2p, we call that WebRTC Direct. And so this multi-adder that you see is essentially connecting to a server that supports WebRTC Direct. The cert hash is how we do like encryption, but without having to rely on certificate authorities. That's why it's inlined into the multi-adder. This is also the case for web transport. And and of course the peer ID of the browser that we're going to connect to. And the fact that it says WebRTC following the P2P circuit, this is like very, very much at the end here, that indicates that it's going to be, that this multi-adder is intended for a direct connection. So it is a circuit relay address, but the WebRTC suffix at the end indicates that like if you click connect, as we will see later, it will actually initiate the signaling protocol because it has all of the information that it needs in order to establish that direct connection. Okay, so those were all of like the sort of fundamental concepts that are important for this. Now we're going to open up the guide, and this is a pretty recent guide that is in the libp2p docs, and we're going to work through it together. So you can follow that in your computer. This is the guide, and as I mentioned, you should have Node.js. You can also have Go if you like. This is like the same diagram but broken down into two diagrams. And okay, we start with this repository, and I'm gonna open that up in my terminal. So there's a lot going on here, but let's start with just the front end. So this is the front end, and I'm going to also open up my code editor and index.js. And essentially all I'm doing here is, you can see, really I have barely anything in here. But this is the create libp2p call. So I'm going to just remove the commented line just so that it's easier to read. And this is all we have here. So we're initiating a bunch of transports here. WebSockets is necessary because that's what we're going to use to connect to the relay. But as I mentioned, it doesn't have to be WebSockets. It could be Web Transport, or it could be even WebRTC Direct. We're going to add WebRTC because that's the transport that we need in order to listen as a browser. And we're going to add the circuit relay transport. That's necessary both if you're just a client using a circuit relay. So if you want to establish, yeah? Yeah? I can repeat your question too.
Discover relay is one. And that question, I never looked up. The question, I never looked up. Discover relay is one. Does it mean it only looks for one relay? What is when I do two? Does it discover two different relays, or I do two, but it's okay still with one? I don't really get the point.
So the idea is that you can actually establish multiple reservations, and you can increase that number, for example, so that you have more reservations. So you increase the success rate potentially.
But this is a physical different relays then, different nodes.
Yeah.
Would it one browser node would discover two different relays?
Exactly.
Okay.
Yeah, Alex?
There's a practical limit to the number of relays that you're going to want to discover. So consider like if you discover a relay, and the relay is listening on Quick, it's listening on TCP, it's listening on WebSockets. That's 3 addresses. So then you'll when you publish as a node listening on the relay, you'll publish a circuit relay address for those 3 addresses. So suddenly you're listening on 6. Well, you're listening on 3 addresses as well. You'll publish a WebRTC address as well. So you're listening on 6 addresses now as the browser. If you discover more addresses, and that's if the relay is listening on a single IP address and port pair. If it's listening on IP4 and IP6, suddenly you have like 6 addresses, then you have 12. Every time you connect to a node, when you run the identify protocol, you send a message with all your multi-adders in it. that message has a size limit. So the more relays you discover, the more addresses you listen on, the more contactable you are in theory. But then if you listen on too many, your identified message will get too big, and remote peers will reject the identified protocol message that you're sending. So you want one or two. You don't want lots. Yeah, so you're obviously, then it's kind of like the tragedy of the commons. You're consuming a lot of resources on the network. So just want to repeat that for the video.
So one is enough.
One is enough.
Okay, so this is what it looks like when I start the front end, and you can see here the peer ID. The peer ID isn't persisted, so every time I reload I get a new peer ID, and also I have logging fully enabled. You can disable that here too, and you won't get it, but for now we'll just leave it. It can get a bit noisy, but it's pretty useful to just see what's going on. I also installed prior to this the libp2p dev tools. But in order to be able to use the dev tools, they need to be able to connect to the peer. And to do that, we need to pass it the dev tool metrics package. And so if I reload it now and reopen up my dev tools, then we should be able to also debug from here the peer. So this is thanks to the work that Alex has done with this dev tools. And we can see that we don't have any peers connected to. Okay, great. Now what we're going to do is we're going to run the relay. So here I have the relay code, and in the relay code I'm also creating a libp2p instance, but this is a node libp2p instance that's going to listen on TCP, not very useful for the browser, and web transport. WebSockets. And I'm also passing the WebSocket transports, making sure that it has noise, YAMX, and this is just a configuration to allow private addresses which aren't enabled by default. And we have identify circuit relay server. This is really important. It has to be a server so that it can allow others to create circuit relay reservations. Gossip sub, that's not critical for now just yet. And AutoNat, which I think I already mentioned. Okay, I'm going to run the relay now, and I immediately output all of the multi-adders. So as we see, single peer ID, multi-adders, and it gets basically one for each transport, for each IP it can bind to. Unfortunately, as I mentioned, the Wi-Fi we're connected to has host isolation, so you can't connect to these to the 10.10, the private IP, but I'm going to connect to the loopback over the WebSocket, which is the first one that is showing up here. Going to go to my browser, paste it in here, and connect. And a number of things happened here. If we filter out for circuit relay, we can see that, first of all, it's logging that it doesn't have enough relays. This is because we set it in the configuration to be 1. And then I believe that after it was able, yeah, there we go, requesting reservation from the browser peer, the one that ends with PW. That's the peer ID at the end here. So it was able to create a reservation. And suddenly our peer has a bunch of multi-adders. So it started off having 0, and then once I connected to the peer and was able to create a circuit relay reservation, it was able to be dialable now on 4 multi-adders. And all of these multi-adders are essentially the circuit relays multi-adders, except that they end with this P2P circuit and P2P, which means that this is also dialable via TCP, not just WebSocket, because the relays are listening on TCP, and both on the private and the loopback. Okay, what's our next step? So we started in the browser, we started the relay, we connected to the relay from the browser. Now, our next step is we want to make the browser dialable. And so we did that already because we enabled the circuit relay transport. But now we want to make sure that it's that we don't have to paste it in every time. And so we're going to hard code this relay that we have as like a bootstrap peer in our browser libp2p configuration. And where would that be? That would be here in the list. So peer discovery list, and I'm going to paste the one that we have here in the terminal. And so if I reload it, it should automatically try to connect to it, and there we have it. Okay, so that's useful. We don't have to type it in each time. And our next step is to actually listen for WebRTC connections. So to do that, we're going to pass in the addresses the listen and the /WebRTC. The reason that we only pass /WebRTC without an address is because the browser never knows its own address. And so we just pass /WebRTC, and then libp2p handles all of the magic sort of behind the scenes to make sure that you're dialable on all of the circuit relay reservations that you have. So if I reload this, something interesting is going to happen. Suddenly we have 8 addresses. So we went from 4 to 8. What just happened? Well, now for each one of these addresses that we had for the circuit relays, we have an additional one that has /WebRTC in the end. So if I search for this, okay. So we can see that we have 4 of these. And the only one that is relevant for us is the one that is over WebSocket and has WebRTC over the loopback. And if I open now another browser window, and again, it has a circuit relay reservation, now I can try to connect to the multi-adder that has WebRTC in it that I just copied, which indicates that it's going to try to use the signaling protocol to exchange the SDP over the relay. And hopefully, if everything goes well, then we have a direct connection between the 2 peers. So in order to verify this, we can see here we should be able to see this also on the other one. So, ta-da! We have both of these browser windows are connected to each other. Okay, I think I can end my workshop now. Sort of. What does this mean like for practical applications, and what else can we do here? The TLDR is that if you're building a browser application, it's a bit tricky to start exchanging these multi-adders. And so this is where we start thinking about how can we do peer discovery? Like, how can these 2 browsers discover each other kind of magically, especially if we consider them to be like ephemeral, right? You have like users with a browser who are just coming and going. Like, how would they find each other? And there's different ways to approach this. The approach that I'm just going to demonstrate here is very much a demo approach. I've been warned multiple times by Alex to never do this in production. I have done it once in production, just for fun, but I mean, it was just a demo. And that is using a pub sub topic where you just on an interval, you essentially emit your own multi-adders. And that kind of works. And the idea there is that in order to have that message relayed, you need each browser to also be able to get that message. And how can it get that message if it hasn't established a connection yet? Well, you can get the relay to also listen to that pub subtopic, and then it will just sort of relay those messages that it gets, because if you have 2 browsers that are connected to a relay, but they're not connected to each other, if they emit a topic that the relay is listening to, it'll pass it on to the other browser. Nico?
This is always confusing to me, this question, but it should be a question of the gossip sub protocol. When I want the relay wants to should repeat a topic, a special topic, right? Is it necessary for the relay to actively republish this message when it receives it, or is the gossip sub it automatically relaying? I think it's automatically relaying.
Yeah, I
as
mean, this
soon
is
as
very much a part of the whole gossip sub spec. So the whole gossip sub spec is built around this idea that you don't have a full mesh of the network. You maintain, I forgot the technical term, but you have like essentially a mesh of, say, 8 peers that you're connected to, and you try to maintain essentially 8 peers that are listening to the same topic. You also have these metadata peers, but you constantly, with these 8 peers that you're connected to, you exchange messages about which messages you've gotten, which ones you already have. And if essentially you share that you want a specific message, or that if another peer sees that you're missing a message, it'll share that message with you. And the thing that it allows is it allows to build these really big mesh networks like Ethereum, that uses it for its consensus protocol, and also Filecoin, where you don't have to maintain a connection to all peers, and it creates a much quieter and more efficient network in comparison to like flooding the whole network with messages all the time.
But it's guaranteed that the messages arrive somehow, or is it possible it's not arriving?
I think it's possible that, I think someone else is better suited to answer that question, and I'm looking at you. What do you reckon?
There are no guarantees. So there are no guarantees. The guarantees like itself, there aren't. But you're assuming that everybody has at least one connection to someone in the net that eventually will get the message. So it's like either you can receive it through the mesh propagation, or eventually every heartbeat you will see that someone got a message that you didn't see and you're going to request it from it. So it's like, yeah, it's like there is no guarantee that you will find something in Kademlia, although it might be there, but same for Gossip Sub. But just assume more or less that 99.9999 of the times it will arrive to everybody after some time, yeah, eventually. Yeah. But something important is that Gossip Sub handles that, and you don't spam someone that sent you the message already. So that's what makes it efficient.
Okay, so to do this, we're going to use this pub sub peer discovery module. And again, not recommended for production applications, but just good for demo purposes. So I think this can be maybe a good kickoff point for potentially having a broader discussion about maybe the ambient peer discovery and how we can approach this in more efficient ways in production apps. I'm going to attend the workshop that Alex is giving later, so maybe that will give me the foundations in order to have another go at implementing the ambient peer discovery protocol. But let's start with this. So we have it here, and we're going to enable it in the browser peer. In the relay peer, we already have it. So we have Gossip Sub, and we're already subscribed to this topic. And the topic is defined here in the constants, and I will make sure also that the browser. So in order to use the pub sub peer discovery, we also need to make sure that we have Gossip Sub enabled. And am I subscribed to this topic? I thought I was. Oh yeah, well, I pass it here in the pub sub peer discovery. Now the relay doesn't need it. It just needs to subscribe to the topic, but it doesn't actually need to have it as, because the relay isn't trying to discover any peers. And if I reload now, then we should be able to see them connecting to each other after a little while. Okay, and whoop, we suddenly see the second connection. So that was it. The browsers discovered each other using this topic. Okay, now as a bonus, I wanted to show that you don't have to use, just to like show the versatility of libp2p, just as kind of like a final point, that you can use a Go relay for this. I'm going to completely shut down the Node.js one. And I can show you the code for this. It's really the nice thing about Go libp2p is just how simple it is to use. And okay, so we have libp2p, and it's listening on a bunch of transports, WebRTC. This is WebRTC Direct, actually, to be specific, and Web Transport. Let's start with just Web Transport for now, which is supported by Chrome. And really, I'm just creating the peer, making sure that it's also circuit relay, that it has circuit relay, and that it's got gossip sub, and that it's subscribed to that same topic, that browser peer discovery topic that we also had in our JS constants. And yeah, that's pretty much it. And it's going to tell us the multi-adders that it's listening on. And we're going to use this one that is dialable from the browser. And for our browser peer, we're going to remove this bootstrap peer that had the Node.js relay peer. And if I go back to the browser and I reload it, it won't connect to anything. If I paste in this web transport and connect to it, then bam, we got these two. Interestingly, didn't connect, doesn't have a loopback. Huh. Ah, that's because I connected to it over that. Over the private rather than the loopback, but I can also connect to it via the loopback. An interesting difference though, that in Go libp2p, it'll only give you reservations over the IP that you connected to, whereas Node.js seems to do it over all of the IPs that you're bound to in the relay. Something that I just noticed now. Okay, but as you see, as soon as I connected to this relay, to the Go relay, because the Node.js one isn't running anymore, they were able to discover each other. Okay, that was nice. I guess as a one final thing, we could also try to do this over WebRTC Direct, because, well, if I open up Safari, Safari doesn't actually support web transport. So I wouldn't be able to connect over web transport. So if I tried this thing, it'll probably fail somewhere. Yeah, great. Okay, so let's try WebRTC Direct. This is still experimental, but it should be stable soon in Go. I believe Go run will recompile. Wait, did I get this right? Oh yeah, got to enable WebRTC and return that line. There we go, we've got a bunch more, and one of them has WebRTC Direct. So I can try to connect to it from Safari. Let's see, what error are we getting here? Okay, maybe I got the wrong one. That looks right. I'm not actually sure why that's happening. I haven't tested this before. But let's try on Safari the Node.js relay, see if we can get that working. Is that the right one? Yeah. So back to Safari, connecting. Okay, great. So it connected to the relay, and let's see if it starts, if it manages to connect also to the, well, these would have to also connect, I guess, to the same relay in order to discover each other. Okay, and I think we're starting to see them connecting to each other. Where's the Safari one? MP. Yeah. No, that's there. Cool. So there we go. We have all of these browsers connecting to each other. Okay, that was pretty much it from my side. You can follow the full guide here, and it like dives into some of the more fine details. But I'll open up if there's any questions.